Welcome back. This is Unit 1, Section 1, Functions and Function Notation, Video 2. Okay, so we're going to get to work. Finding input, grab a pen, finding input and output values of a function. So evaluation of functions in algebraic form. So let's suppose I gave you x squared plus 3. So let's suppose I gave you this function and I want you to find x equals 2. We can just plug that 2 in right there for x. Minus 4. We keep simplifying. Equals 6, and we would say f of 2 equals 6. Now, being weird, what if I just let it be a? Well, that x now becomes a. And wherever x is, you plug a in. And that's it. That's your answer. Super simple. That one's the easiest. Now this one. What if we let it equal a plus h? Well, that x now becomes this entire thing, a plus h, which means everywhere I have an x, I'm going to put a plus h. And I'm going to keep carrying this out. So a plus h squared is going to be a squared plus 2ah plus h squared. You can, if you have not memorized that, that's totally okay. It takes a while to memorize it, a lot of practice. You could pause the video, here and take the time to multiply it out. I'd recommend it. Plus 3a plus 3h, I'm distributing that 3, minus 4. Now I can combine like terms. Can I? Oh no, I can't. Notice how the exponents I have don't match any other ones. I don't have another AH, I don't have another A, I don't have another H, so I would just rewrite this. Actually, I'm not even going to bother rewriting it. You could just leave it like that. So evaluating functions expressed in formulas. So let's say I gave you the formula 2n plus 6p equals 12. And I want this in the form p equals f of n, which means I want p on one side by itself, so that if I know n, I can plug it in and find p. Now from this equation, I'll go to a different color. I'm going to subtract 2n from both sides, right? Because it's, positive 2n, so I have to subtract it. That gives me 6p, 12 minus 2n. Now I'm going to divide both sides, so every term, by 6. And that gives me p is equal to 12 divided by 6 is 2. 2 over 6 is actually 1/3. N. And this is this. There we go. And it can be evaluated just like all of these above here. Another familiar way that you guys will see it in textbooks is like this. That's popular. That would be popular. Evaluating a function given in tabular form. So what that means is that if you're given this, it'll either be y or sometimes it's f of x. They're the same thing. So this is 1, 3, 5, 7, 9. This is 2, 4, 6, 8, 10. So if I want when x equals 3, that would be this value right here. If I want f of 7, that would be this value right here. It's 8. Now values from a graph. Say we have this graph. I want to know when x equals 3. I would just go look at where this point intersects, and that's going to be my y. Most of you guys should be familiar with at least finding these types of values for functions from a table or a graph. Determining whether a function is one-to-one. So for each output, there is one input. So you guys remember PQ, M, N, R. Okay, right, wait. Yeah. So you guys remember this, right? This is a function, correct? Well, it is not one-to-one. Now, one-to-one would be something like this, where there's literally 1 to 1. Each output value, so each output value corresponds to exactly one input value. So, no sharing here. They do not like to share. And that's what one-to-one means. So here, we're going to do this one. Is a balance a function of the bank account number? So remember, the bank account number becomes the domain, the balance becomes the range. So let's say we have, for the domain, and then we have range. So let's say we have bank account numbers. Number 1, number 2, number 3, number 4, because that's our domain. Now let's say we have balances. Balance 1, balance 2, balance 3, and then that's all we're given. So what that means is that maybe these two guys have the same balance. Notice the point I'm making is that each bank account number can only have one balance. So you can't have number 2 have a balance of 1 and a balance of 2. It's like, what does that even mean? So is a balance a function of a bank account number? Yes. Is a bank account number a function of the balance? So now, for the domain, we're going to have balance 1, balance 2, balance 3. Let's add some more balances. For the range, we're going to have bank account number 1, bank account number 2, bank account number 3, bank account number 4. Now, if they all have different bank account balances, then that's one thing. But let's say a balance is the same in two bank accounts. Well, that's not okay. So in this case, your answer would be no. So I'm going to say in general, your answer would be no, since it is possible, given an incredibly large amount of people, that you could possibly have the same value in two bank accounts. Is a balance a one-to-one function of the bank account number? Well, I would say no. Oh, wait. We are now looking at A, because balance is the range. So is the balance a one-to-one function of the bank account number? So does that mean that for every output value, there's one input value? Well, if you share a bank account balance, then no. So no, it isn't. If each percent grade earned in a course translates to one letter grade, is the letter grade a function of the percent grade? So, if each percent grade earned in a course translates to one letter grade, is the letter grade a function of the percent grade? So, letter grade a function of the percent grade. So our range is the letter grade. Oh, I guess I don't have E at Richland. F. Or I guess they also have W, right? Or an I. A function of the percent grade. So the domain is going to be the percent grade. So we've got a 58, a 70, a 71, a 60, a 90, an 85, a 77, 93. All right, these are all of them. So let's start matching up some things. Well, a 58, that's a failure, guys. Oh, I'm so sorry. A 70 be a C, a C, which is another C. 60 is a D, 90 is an A, 85 is a B, and these are just grades I made up. Another C, another A. Wow, that got messy real quick, didn't it? But the point we are trying to make is, do any of these single percents go to multiple letter grades? No, they don't. So this is a function. Yes, it is a function. Now it wants to know if it's one-to-one. The answer is no, not one-to-one. And why is that, you may be wondering? And that is because the output values in the range can go to multiple different input values, which is not what we want for one-to-one. So using the vertical line test, so you draw a vertical line, right? How many times does it intersect? Is it 1 or greater than 1? So if it intersects one time, then you're good to go and you have a function. If it intersects more than one time, you're not good to go and you don't have a function. So for example, let's take this guy, right? Any line I draw, any vertical line I draw, will only intersect this graph once. So it is a function. That is a function. Now let's have a look at this guy. Weird, right? I know. And let's draw all these vertical lines. Super vertical lines. Oh no! We're running into problems. Look at this, and this, and this is a problem, this is a problem, this is a problem, this is a problem. Oh my gosh, look at how many times it intersects this graph more than once. This is not a function. And that's what the vertical line test tells you. What about the horizontal line test? Well, let's have a look at this bad boy, the one from last time. It is a function, right? So the horizontal line test tells you, is it 1-to-1? And the answer is, if it intersects one time, yes. If it intersects more than one time, no. And that is because, do you remember every output value, which is this axis, can have only one x value associated with it. So what that means is that any horizontal line that you draw the problem is at this value, it has three values of x associated with it. So this is not 1-to-1. But notice that it is still a function. So, you know, it's not all bad. Now let's have a look at, let me think of a function. Let's have a look at this function. Continually increasing function. I'm going to draw a bunch of horizontal lines, right? And you know what? It looks good. This function is 1-to-1. Notice it also passes the vertical line test, so it is a function. I can show you guys that right here in blue. So it is 1-to-1, and it is a function. So identifying basic toolkit functions. Now, toolkit functions is a term. You may have heard parent functions. So if you had to imagine that a mathematician was somebody who could actually build things, physical things, with the stuff that we do. So we facilitate others in building physical things. So it's not that we don't do anything. We just help people know if it's even possible. So, you know, whether or not it'll be in vain. But let's say if we wanted to do something solid with mathematics, like if we could pull a 2 out of our backpack, let's say. So these toolkit functions are the functions we use to build math, to build the everyday functions that you will see in this class. There, I believe, are 9 of them. So the constant function, f of x equals c. That's just a y straight across. So if you saw plus 12x plus 6, right? This is a constant function. So you could say that this is some piece plus the constant function. This is the identity function. It identifies as itself. So whatever you put into it, you will get out of it. Notice that. If I put 1 into it, it's going to be 1. If I put 20 into it, it's going to be 20. If I put negative 20 into it, it will be negative 20. So let's say we had f of x equals x plus 1. Notice that this is the identity and this is the constant function. This is actually two functions. Now the absolute value, this is the stabby graph. It's the sharp pointed, very pointed, very pointed graph. Just right down there to a point there. You don't see it too often. It's very important to know. So this says that whatever value you put in, you're going to get the positive value back. So if we put a positive value in, of course we're going to get a positive value. But if we put a negative value in, these lines, those two lines means that you're going to get a positive value back. So this is a quadratic, x squared. Anything with x squared in front will get you a parabola, which is what this graph is. So anything really. And notice that this is the quadratic parent function. This is the identity. And that is a constant. Now let's have a look at a cubic function. So this is like an S-shaped function. This one can take in negative values and return negative values. Now the reciprocal function, that is 1 over x. This is the function that has sort of two graphs, if you would, just put together, but it's a whole graph. That graph is 1 over x. And you've got this asymptote here. So it will never touch this axis because this x can never equal 0 because we can't have 1 over 0. Notice that as x gets larger, f of x equals 1 over x gets smaller. So as x gets smaller, so like a fraction, then f of x gets larger, like this. 1 over half equals 1 over 1 divided by 1 over 2. And of course, rules of dividing fractions. You keep the first one, flip the second, and multiply, so it's just going to equal 2. Notice it's large. So our next one is the reciprocal squared. So this is just like the reciprocal, but it's just a top portion. So it cannot take on any negative y values. Notice that f of x has got to be greater than or equal to 0. Or greater than 0. It won't really equal 0. Square root. This is just 1/2 of a parabola on its side. Notice that if I were to complete the other half, right? Well, that's not the case. This is the square root of x. Notice x is only positive we cannot have a negative x, and y, so that's your f of x, is also positive because you cannot have it be negative. Here's the cube root. Notice you can have both positive and negative. Notice that you cannot have, if you have a negative input, you cannot have a positive output, and if you have a positive input, you cannot have a negative output. That's what this graph says. Okay, that concludes Unit 1, Section 1, Functions and Function Notation. If there are any questions, you can email me, and I will see you in the next one.